Welcome everyone to this week's BAIR CPAR BDD seminar. It is my pleasure to introduce Chang Liu, who's a postdoc with Professor Don Song. He was previously at the University of Maryland, College Park, and has won a long list of awards. But please, Chang.
Yeah, thank you for the introduction. So hello everyone, I'm Chang Liu. So I'm very happy to here to share our recent work on using neural network-based approach to do vulnerability detection. So let me give you some context first. So today, there are more and more Internet of Things available to users, right? So they could be cell phones, they could be smart home devices, they could be even in the smart cars, right? Which are in the autonomous driving systems. Okay, there is a prediction that in the next few years, there will be over 50 billion Internet of Things devices available to on the market. So that's a huge number, right? So the security issue of these IoT devices will be very prominent. Okay, so one of them is the vulnerability in firmware images. So on all IoT devices, they are operated by firmware images, but they are operated by firmwares. You can consider that these firmwares as the operating systems to these IoT devices. So when vulnerability is found in these firmwares, then the security of these IoT devices will be very important, right? So then why vulnerabilities are easy to find in these firmware images? So consider this is a firmware, which is kind of a collection of software packages operating over the underlying hardware, right? So many of the components are quite standard. Like one of the components is these secure communication devices, because all of the IoT devices need to communicate with each other through a secure channel. Therefore, the OpenSSL library, so this is just one example, the OpenSSL library will be frequently used in almost all, in the majority of these operating systems. However, there are more, so for every period of time, there will be a new vulnerability discovered in this library, because they are open source, so everybody can test it. For example, one of the most prominent example is the heartbleed, right? So once that is found, not only firmware images, but not only IoT devices, but all services globally are affected by this heartbleed vulnerability. So an important problem is that once a new vulnerability is released, then how can we quickly detect the vulnerability, whether they exist in the firmwares or not? So that if a vulnerability is detected to exist in a firmware, then we can fix that potentially with an update or a patch, right? So the most important first step is we need to detect this vulnerability first. Okay, so here is the question. So when a newly discovered vulnerability is available, for example, a code sample is provided, like some certain kind of code pattern is not safe, then how can we efficiently locate whether a given binary code is affected or not? So here the binary code represents the firmwares. Okay. So for this problem, we delegate that into a code similarity problem. That is, given two binary code, if we can detect whether they are similar or not, then we can very easily solve the vulnerability detection problem. So here is a simple solution. So for example, we already have the code similarity detection algorithm. Then we can simply scan through the entire database of the firmware images, right, which contain all the binary code used in firmwares. And then we can look for those code snippets that look very similar to the to the vulnerable code samples. Then if we found any, then we can say that, okay, this is potentially a vulnerable code. Okay, so this is the problem setting. So the problem we want to solve in this work is we want to detect whether two binary code snippets are similar or not. And there are a few challenges. The first problem is that the binary code could be in different platforms. Because there are so many different firmwares, they could be using all different kind of ISAs. They could be in x86, they could be in ARMs or MIPS. So all different architectures, the code will look very different to each other. So this will impose a very big challenge to how can we detect whether two code snippets in different platforms are similar to each other. Okay, so and second, so even though two code snippets are in the same platform, it is still very hard to judge whether two codes are similar or not, because similarity is a very subjective term. I will show you an example when some codes are considered to be similar and some code should be considered to be similar and not similar based on the concrete application scenarios. Okay, and third, we need to handle a large scale of data sets. That means because there are so many IoT devices, we want to have an efficient algorithm so that we can detect as many vulnerabilities as possible in those firmwares, right? So in this work, so we solve this work using a neural network approach, but wait a minute. So before we talk about our concrete approach, we want to know why do we want to apply neural network to this problem, because binary analysis is typically using compilers or program analysis to do the job. So why do we want to use neural networks? Okay, so I will give you some examples to show why neural networks have unique advantages over the non-neural network approach. So the first example is this. So right now I gave two code snippets. So both of them are in source code for you to easy to read, but they could be compiled into binaries. Okay, so what's wrong with these two code snippets? So I want you to think a little bit whether they should be considered as similar. So actually we have two application scenarios, for example. One is we want to detect, for example, there are homework submitted from students. If we want to detect whether one is copied from the other, then in this scenario, we should consider them as similar because only one line is different, right? But in the other scenario, if we want to detect whether the vulnerability is fixed or not, then these two code snippets should be considered dissimilar. Why is that the case? Because in the first case, the end of, for example, when A is representing a string, then the end of A is not written with a 0, which means the end of string. Then this will cause a memory buffer overflow or similar attacks. So this is a vulnerability. But in the second case, because after the for loop, we write a 0 into the end of the string, then the bug is fixed. So in this application scenario, we should consider these two codes are different because the later one, the bottom one, fixes the vulnerability, which appears in the first one. Okay? So using a non-neural network approach, the traditional approach typically manually design some heuristics to do this similarity detection. So this heuristic can only work in one scenario because given these two cases, the same approach can only detect whether it is either similar or not similar. So they cannot adapt to the two different application scenarios in our setting. So using a neural network approach, we can mitigate this issue. And the second issue is that it is more efficient. So here I will give you so I forward reference some example that I will mention in the following, But typically, when you want to detect whether two co-similar, you will convert them into two co-graphs. And then the main task is that you want to detect whether two co-graphs are similar or not. Then one approach is that you can use graph matching algorithms to do the job. However, a graph matching algorithm is very expensive. That is typically cubical to the number of vertices in the graph. Okay, so these algorithms are very slow. And using neural network approach, we show that there is a dramatic speed up in terms of efficiency. So I will explain why this is more efficient in the following discussion. But before we move forward, I want to provide two takeaway messages. The first is that our work is one of the first ones to demonstrate that deep learning technique can be used in these binary analysis tasks, which are typically done by program analyzers. And for the second one, we hope that our work can foster more investigations into this field to apply deep learning technologies into binary analysis. Okay. So right now I start to explain our approach, and then I will explain the details of our network construction. Okay, so basically what we want to do is that we are given two binary code. Maybe one represents the the binary code in the firmwares, and the other represents a code sample of the vulnerability. Then we can use a disassembler to extract them into a code graph, which is typically a control flow graph. Each node represents a vertex block, code block. And then we can convert them into a graph with each node using an attribute vector. And then our embedding network will convert the code graph into an embedding. And this is the core work of this paper. And then after the two code graphs are converted into the embedding, we can detect whether they are similar or not based on the distance function, for example, the cosine similarity function. Okay, so this is the basic workflow. And as I mentioned, the most important part is in this embedding network. Okay, so here I want to emphasize again the difference between our work and previous work. For this, for using previous work, for example, this state of the art is last year's CCS paper. They use a bipartite graph matching algorithms. And the problem is that they are very slow, and the effectiveness is limited by this bipartite graph matching, as I mentioned. Using our approach, we design a deep graph embedding network, and then this network can extract features automatically from the code graph, so that no manual tuning is required. And then we combine different approaches to train this graph, so that the features, the embedding vectors generated using this approach can be very effective. Oh, okay. So this is the high-level overview. So given a code graph which looks like this, is a directed cyclic graph, and then on each node there will be a so-called attribute vector, but I don't want to go into the detail of that. And then the embedding network will convert that into an embedding vector. Okay, so this is the end goal, and how do we really achieve that? So basically, this is you can view our algorithm as an iterative graph propagation algorithm. So initially, every vertex has an attribute vector, as I mentioned multiple times. So, and then in each iteration, these attribute vectors and the embedding vectors on each node will be propagated to its neighbors. Okay? And then after several iterations, for example, in this figure, there are t iterations in total. So each vertex will have an embedding vector that will contain the structure information of the graph. And then all the embedding vectors on each vertex will be aggregated together using a summation operator. And then through a fine transformation, then we get the final final embedding of the entire graph. Okay, so then here there is a subtlety, that is how do we really do the propagation, right? For propagation, for example, we assume that each vertex has a initial attribute vector xu, and then so we basically aggregate all the adjacent vertex embedding features together and then feed that into a multi-layer network, neural perception network. And then later we will combine that together using another one-layer feed-forward network, fully connected network, and then to compute the next the aggregation results. Okay, so this is the network structure, and then the key problem is how to train this network. Okay, because traditionally this network is inspired by the structure-to-vec work, which was originally used for a classification problem. For example, for a graph, you want to classify which class the graph belongs to. But in our setting, we don't have these we don't have these classes of labels. So we need to develop a new approach to train that. So our approach is to use a synonymous network to train, given two instances, whether they are similar. If this is the case, then the cosine similarity should be close to +1. Or if two instances are dissimilar, the cosine similarity of the embedding should be close to -1. Okay, so inspired by this approach, we can have two kinds of training method. One is so-called application-independent pre-training. That is, we propose one method. For example, given the same source code, we can compile them into different binary formats, using different compilers, using different platforms, and using different optimization levels. And then for two binary functions compiled from the same source function, we will label them as similar. And for other pairs of binary functions, we label them as dissimilar. Okay, in this way, we can give the supervision. Okay, so you can see that this is application independent. For example, this approach cannot capture the information like I showed before, like whether two codes are similar. If we consider the cheating scenario, they are similar, but if we consider the vulnerability detection, they should be dissimilar. Okay, then how can we do that? So we also allow this application-dependent retraining approach. That means human experts can provide some additional labels. These labels could be very few compared to the first application-independent training set, but these labels should be should be incorporated during the training, so that the finally learned embedding network can reflect all these labels. Okay. So, right, this is the approach. So in the following, I will show some experiments. I will show some results. So one is that this figure illustrates the visualization of the embedding using TSNE. So basically, we show 5 different source functions, and then we compile them using different, as I mentioned, using different compilers, different optimization levels, into different platforms. And then in this 2D plan, we can observe that those binary functions compiled from the same source function are very close to each other. They are clustered based on the source function name, right? So this demonstrates that our embedding network learned from this application independent setting is very effective at generating this embedding. Okay, then later I will show some performance experiment. For example, in previous work, to check one similarity detection, to solve one similarity detection between two code graph instances, the previous work, as I mentioned last year's CCS paper, that will take a few seconds to a few minutes, right, which is very slow. But using the as I mentioned, most of them are because of graph bi-party graph matching. But using our neural network, we only need a few milliseconds. The reason is because that our computation of the embedding is totally based on only one input graph. So there is no graph matching computed at all. So the embedding is computed very efficiently, and also the distance between two embeddings can also be computed very efficiently because that's just a cosine similarity. Okay. Also, this is the serving time. So that is 2,500 to 16,000 times speed up. That is 3 to 4 orders of magnitude improvement. Also for the training time, that is also a dramatic improvement. For example, in the previous work, it will take more than 1 week to train their model. They are using a clustering algorithm to train the model. Okay, and then in our work, to train one effective network, we only need less than 30 minutes. So that is much more efficient than previous work. This also allows us to retrain the model multiple times within a short period of time. Okay, so the last experiment is about the effectiveness of our approach. So we use that to, so we collect a large data set which contain over 400 million binary functions. And then we want to identify the top 50 results. The top 50 most similar results to a vulnerable code samples. And then in the previous work, they show that only 10 out of the top 50 are indeed vulnerable code. However, using our approach, we can confirm that over 42 out of the 50, that is over 80% of accuracy, can be confirmed as a true vulnerability. So this demonstrates that our approach is also much more effective than previous work. Okay, so that's all of my work. So the main takeaway message is that using deep learning approaches can be not only more effective but also more efficient to learn embedding functions for binary codes. And also, we want to mention again that program analysis can be a novel application domain for deep learning approaches. Okay, thank you very much. I'd like to take questions.
Thank you. We'll take questions now, but let's please wait for the microphone so that remote audience can hear. Any questions?
Hi. I was wondering, how do you ensure that the neural network that you end up training generalizes to arbitrary code graphs?
Yeah, so this is a good question. So I don't show the experiment here, but I don't show the experiment results here. But actually, all the binary functions in here are do not appear in the training set. So this is a experiment done on the unseen data. Right, so and we also have this controlled experiment where we manually split the training set and test set to make sure they are not overlapping with each other. And then we evaluate on the test set, the performance is also better than previous approaches. Yeah.
Any other questions? If not, let's thank our speaker again.
Yeah, thank you everyone.